Hi, Algebra 2 Honor students. Today is going to be Unit 17, Day 2. Today we are talking about more sets and probability within some set notation. So what is a set first and foremost? Well, a set, very simply put, is a collection of elements. Okay. So those elements can represent a wide variety of things depending on the context, but what is exactly an element? And elements are just different items that are in a set. So we're going to be looking at different sets today, and within our sets, if we have two sets of information, maybe we'll look at what's on the intersection of those sets, what is in the union of those two sets, things like that. So set W is defined as the collection of all integers that are greater than 0 and less than 10. Write out set W in roster form. So roster form is just a list with curly brackets. So I would say set W equals, well, greater than 0 and less than 10, the notation there means that those aren't included. So it'd be something like 1, 2, 3, 4, 5, 6. Carry my set down here. Set W in roster form might look something like this, just as simply a list of the numbers that are elements of that set. Then it says show set W with a Venn diagram. Well, a Venn diagram, I usually think about two different sets, and there may be some intersection in between, although they don't have to intersect. But because we're only talking about one set of information, set W, we'll do one circle with all those elements in it. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Not the most exciting Venn diagram we've ever seen, but starting to build that concept there. Part B says define a set C that is a subset of set W, then list the elements of set C. Now, there are so many different subsets that you can define. You can pick really whatever you want, but just keep in mind that when you define a subset, all of the elements you choose have to be in set W somehow. So let's say I say that set C is the integers from 2 to 5 inclusive. Okay, and that term inclusive, hopefully you would take that to mean that we're including those endpoints 2 and 5. So therefore set C is 2, 3, 4, and 5. So that's the way I've defined it. And then what is the intersection of W and C? Explain why you and your classmates have the same results. Well, what you should find, and I know we're not doing this in class, we're doing this in the video right now, is that the intersection of W and C, and as a reminder from yesterday, that's what that notation looks like, is anything that these two sets have in common. So if you were to draw another Venn diagram, like what would go in the intersection there? Wouldn't it actually be all of those elements right there? It would be 2, 3, 4, and 5. And that's always going to happen when one is a subset of another. Okay, so we just get set C again because we know that C, and I know it's a little bit tough because the subset symbol looks like an elongated C, but I'll try and make it really pronounced there. C is a subset of W. So it makes sense that when I find the intersection with set C and set W, that it's just going to be essentially what set C looks like there. As you can see, I've already noted that we'll do this one in class. This is going to be an experiment where we toss a coin and then we roll a 6-sided die. And we're going to note some outcomes based on that. So we talked about that a little bit, but you know what? We'll save that for a warm-up in class next time we're together. If we go to the next page, we see that we have a definition of an empty set. An empty set is a set with no elements in it, which makes sense based on the fact that we're defining it as being empty. The notation for empty set, we have two different notations, and this is something that we've seen for a long time now. Notation can either be this for empty set, or you can open a curly set of brackets with nothing on the inside. Okay. So moving on to example 3, draw a tree diagram that represents all the outcomes in the sample space of rolling 2 4-sided dice. So we're going to roll 4-sided dice, which I realize we're typically used to seeing 6-sided dice, but for this example, we'll think of it as 4-sided die. All right. So when you roll it, you can get a 1, a 2, a 3, or a 4 the first time on the first dice. Now, since we're rolling 2 of those, if the first one has a 1, the second one could have, from there, a 1, a 2, a 3, or 4. And that's going to happen as a branch from each one of those first die options. Okay, if the first die has a 1, 2, 3, or 4, the second one could be a 1, 2, 3, or 4 from there. Okay, so how many possible outcomes are there once we fill in that tree diagram? Well, it looks like if I look at the end of the branches, each of these for the first die plus the second die, there'd be 4 options here, 4 options there. It looks like a total of 16 potential outcomes in the sample space. And part B, what is the probability that you do not get the same number? So probability of not getting the same number twice. Well, that's going to be excluding 1, 1, 2, 2, 3, 3, and then 4, 4. And there's a few different ways you can write that final, is that you can say, well, that's just going to be 12 out of 16, okay? Or you can think of it as doing 1 minus all the possibilities where they are the same. So there are 1 out of 4 chance, okay, of getting, or 4 out of 16, right? Of getting the same number twice. So 1 minus 1/4. It's pretty likely that you're going to roll 2 die and that they will not be the same number. About a 75% chance of that happening. Okay. What is the most likely sum of the dice? And then what is that probability? So if we were to look at the sums up here, 1 plus 1 would be 2. I'm going to write the sums in red. So let's see, that would be 2, 3, 4, 5. And then if I go to the second set over here from this tree diagram, we would have 3, 4, 5, 6. And then we would have 4, 5, 6, 7, 5, 6, 7, 8. And if you look at all of those sums, if you can squeeze that all in there, there's only one sum that comes up in every single one of those pairings. And the only sum that comes up every single time is a sum of 5. Okay, so a sum of 5 can happen in 4 different ways. The most likely sum is a sum equal to 5. The probability that the sum is 5 is going to be, well, we saw that happen 4 times out of 16, which again, of course, reduces to 1/4. That's all we're talking about there. All right. Example 4, a couple more examples of probability, and then we're going to move on to some set notation. What is the theoretical probability of drawing a teal marble from a bag filled with 5 teal marbles and 7 pink marbles? Pretty easy, but I just wanted to make sure that we understand theoretical probability is, in theory, what should happen. It's not necessarily that we're doing trials. That would be an empirical probability. So let's see, we have 5 teal marbles and 7 pink. So probability of getting a teal is going to be that we have 5 of them out of a total number of marbles in the bag of 12. 5/12 would be the probability there. And finally, one more quick example. A group of boys is on a hike. You take a random sample of 10 of them and find that of those 10, 6 of them are wearing shorts. What is the experimental probability of a boy in the whole group wearing shorts? So experimental probability is we're looking at the data within our group right now. And because 6 of the boys are wearing shorts out of 10, that would have to be the probability that a boy wears shorts. Okay, it's just specific to our random sample of 10 students. Okay, it's not saying, the probability in the whole world of these boys wearing shorts. But anyway, that would reduce to 3/5 if you want to reduce it, about a 60% chance of picking a boy that wears shorts in our group that we're hiking with. All right, so the next page, on page 10, by the way, of the packet, this is going to be a save for class. So now we're looking at some Venn diagram examples where we're going to start shading in some of these regions based on really 2 different sets. We have F is that we have works of fiction, and then E is if something's available as an ebook. We're going to talk about that next time we're in class. Let's actually do another Venn diagram example on this page. And it says when a fish is selected at random from a tank, the probability that it has a green tail is 0.64. The probability it has red fins is 0.25. And the probability it has both green tail and red fins is 0.19. So if we kind of write that down in summary, probability of green is 0.64. The probability it has those red fins is 0.25. And the probability it has both, which I'm going to use that notation G and R, is 0.19. Draw a Venn diagram to represent the information here. Okay. So here's what we're going to do for the Venn diagram in terms of probabilities. In the intersection, the very first thing I want you to do is put 0.19 in the middle. The probability that it has a green tail and red fins has to go right there. Then from there, you're not going to put 0.25 where you see red, because the whole red circle has to add up to 0.25. Okay. So what we're going to do is the probability of just having a red fin and not a green tail would be 0.06. Okay. Again, these two things have to add up to 0.25. So simply take 0.25 and subtract out that intersection. Similarly, over here, I'm not going to put 0.64 here. These two numbers have to add up to 0.64. So if I do 0.64 minus the intersection of 0.19, I know that we have 0.45 is the probability of just having a green tail. And once I have this filled in, I think these questions are going to be pretty quick for us to answer. But let's go ahead and add up what we have so far. 0.45 plus 0.19 plus 0.06 is a total of 0.7. So we've only accounted for 70% of our cases so far, which means that there's another 30% out there. And what that means is that 30% is outside of the Venn diagram completely. These are the people that do not have green tails or red fins at all. So if it has neither of those two, that's going to live somewhere outside of our Venn diagram. Okay. Let's see if now that we have this completed correctly, we can fill in some of the information below. Find the probability that the fish has red fins but does not have a green tail. So notationally, what you might see for that is the probability of red fins and no green tail would be the complement of the set with green. So we want red but no green. That looks like it's going to be this value over here, 0.06. So again, once we already have that filled in, it's going to be pretty quick. How about green tail but no red fins? So now we want green and the complement of red. Well, that's going to be our 0.45 that we wrote just in that section. And finally, because we've already done this, this is going to go quickly, neither a green tail nor red fins. So it doesn't have either or. That's our probability on the outside. So the way we found that is we calculated 1 minus 0.70 to get a probability of 30% that will happen. And yeah, I think that's it for that section. Last but not least, we have complete the table below showing the probabilities of the events corresponding to the cells of the table. Okay, so what we want to do is we want to look up above and basically translate this information into a table format. So what's the probability that you have red fins and a green tail? Red fins and green tail is definitely 0.19. And the probability of red fins but no green tail, red but no green, is 0.06. For a total of 0.25. And that kind of makes sense, okay, because we know that the probability of red in general is 0.25. All right, not red, but we have green. Well, not red, but green is 0.45. Then we have both here, not red and not green. Not red and not green is 0.3 on the outside there. And that's a total of 0.75. Okay. Let's kind of add going down here. The probability of green in this case was 0.64. Okay, that was given up above. All right, this column would add up to, for not green tails, 0.36. And finally, your totals adding across should equal the same. And not only should they equal the same, they should equal 1.00. We should have accounted for 100% of the fish in this specific tank that we're looking at here, which is exactly what we have when we add up these totals. So a variety of ways to represent the info. We can have it in a Venn diagram. We can have it in a two-way table like this. We're going to see both of those used pretty frequently in our probability unit. The last example on page 12, we are going to save this for class. So go ahead and leave that one blank. A couple things that we'll do in class next time we're together. So if you have any questions about this, let me know. Otherwise, have a great rest of your day.